The heaviest elements in the universe originate in the high-pressure environment of stellar collapse, though today we force them into existence inside particle colliders. This historical periodic table highlights a structural anomaly, the bottom-most section where the rare earths and actinides are physically detached from the main grid. This separation marks a boundary line in how physical laws govern atomic behavior. This highlighted bottom row consists of elements 89 through 103. These 15 elements make up the Actinide series, and they share a defining physical trait. Every isotope in the group is radioactive. This row provides a structural record of humanity's increasing technical control over nuclear physics. As the atomic mass increases from left to right, the series transitions from naturally occurring energy sources to engineered synthetic atoms. The series demonstrates how systematically adding protons changes an element's role, from generating gigawatts of electricity to testing the absolute physical limits of the periodic table. This is a data map of the actinide row. Starting with element 89, actinium, the data curve shows a stable half-life, used today in targeted nuclear medicine. Moving to element 90, thorium provides the thermal density required to power advanced nuclear energy architectures. Element 91, protactinium, functions as a natural timekeeper, allowing physicists to trace the evolutionary stages of heavy elements throughout the cosmos. The sequence culminates with element 92, uranium. Forged in exploding stars, it sits on a massive peak of radioactive stability. Uranium drives modern civilization by providing the raw power required for municipal electrical grids and long-range deep space exploration. These first 4 elements represent a primordial phase where human intervention is limited to harvesting the massive energy already present in the natural world. This dividing line, dropping between elements 92 and 93, marks the transuranic threshold. This is the point where naturally occurring elements end. Elements past this threshold are no longer found in the Earth's crust and must be engineered inside nuclear reactors. Element 94, plutonium, generates a predictable, long-lasting thermal decay. That heat profile provides the necessary power for robotic probes operating in the deep shadows of the outer solar system. By contrast, element 95, americium, performs a hyper-localized role protecting millions of lives in ordinary homes. Its quiet, steady radioactive decay ionizes air molecules, providing the mechanism required for modern smoke detection. Crossing the transuranic threshold shifts the focus from powering entire cities to engineering precision radiation for specific technological challenges. Element 96, curium, serves as a specialized power source for scientific instruments deployed on off-world rovers. Named for Marie and Pierre Curie, this element connects these synthetic isotopes to the history of radiation research. Element 97, berkelium, acts as a target material. Scientists bombard it in colliders to synthesize even heavier atoms. Element 98, californium, is one of the universe's most powerful neutron emitters. This intense neutron flux penetrates dense materials, allowing scientists to image internal structures that ordinary light cannot reveal. By element 98, the series provides volatile, highly specialized tools designed to manipulate matter and light. This data curve shows the final 5 slots of the F block. At einsteinium and fermium, the half-life plummets to near 0, indicating a transition toward total instability. These ultra-rare isotopes exist for seconds or minutes, serving as probes to test the ultimate physical limits of the periodic table. Einsteinium honors the physicist whose work redefined our understanding of atomic energy. Element 101, mendelevium, is named for the architect of the periodic table, marking the shift from theoretical chemistry to laboratory reality. Nobelium represents the search for the heaviest and most extraordinary atoms that can be forced into existence. The series ends at element 103, Lawrencium, the final position of the F block. These final 5 isotopes exist as fleeting measurements, proving that the atomic nucleus can be pushed to its theoretical breaking point. This complete diagram of the Actinide series reveals a clear progression. The row transitions across 3 distinct stages: natural energy, engineered utility, and theoretical frontiers. The series charts the movement from discovering ancient natural power to the active engineering of synthetic physical realities. Lawrencium concludes the F block, establishing the structural foundation required to move into the super-heavy frontier.